So we will continue talking about decomposition methods. In this lecture, we will cover Lagrangian relaxation and decomposition. So this method is quite related to some of the lectures we talked about before. Remember, we have a lecture on Lagrangian dual, right? I give you a convex problem. How do you take the Lagrangian dual of that convex problem? Perhaps you still remember the Lagrangian dual of a quadratic constraint quadratic program is a semi-definite programming problem. But for that problem, you have a closed form. For mixed integer programming problem, taking the Lagrangian dual is not that trivial, so that's what we will cover in this lecture. The other connection with the previous lecture is with Danzig-Wolff decomposition. So they are both targeting problem with so-called complicating constraints. So if you remember from the previous lecture last Thursday, we discussed something called Danzig-Wolff decomposition. Right? It's related to column generation, where you have, let's say, x1, x2, xt. These are t blocks of variables. And then for each of the block, you have some linear constraints. Right? With all the xi's are all the x1, x2 to xt are greater than or equal to 0. So each of these blocks are in standard form. Okay. If you do not have these so-called complicating constraints that involves all the blocks, then each of the block is decomposable. Right? Remember what we did in the previous lecture is we are representing the problem using Minkowski well. Right? For each of these blocks, we represent each block as a conic combination of extreme rays and plus convex combination of extreme points. And then these complicating constraints is written in the convex combination and conic combination form, right? And you start with only a few extreme points and extreme rays. Then you solve a pricing problem to determine whether you should add additional columns to the complicating constraints. Okay, yeah, that's what we did in the previous lecture. Now, how is Lagrangian relaxation related to the Danzig-Wolff decomposition? You will find out in this lecture, Lagrangian relaxation is a dual form of Danzig-Wolff decomposition. Okay? And you will show that in your homework. So now, before we go to this theory, let's give you some motivating application, right? Because at the end of last lecture, we just briefly talked about Danzig-Wolff decomposition. We didn't even cover what type of application will follow this particular form. Right? So in general, you will apply Danzig-Wolff decomposition or Lagrangian relaxation to problems with so-called complicating constraints. So in this formulation, this constraint is a complicating constraint. Right? If you remove that constraint, all the problem can be solved easily. They can be decomposed by 1, 2, 3, all the way to t. So I will give you two motivating applications of problem with complicating constraints. So the first application is two-stage stochastic programming. Right? So we talk about this in the Bender's decomposition lecture. Remember, the idea of two-stage stochastic programming is that you have some first-stage decision x. X satisfies some linear constraints, and then you have so-called second-stage decisions y omega, where for each of these scenario omega, you have a set of constraints. Right? Now, remember in the Bender's decomposition lecture, x is so-called complicating variables. Right? If you in this problem, if you fix x, all the y's can be decomposed by each scenario omega. Right? So that's why x is called the complicating variables in two-stage stochastic programming, and you can apply Bender's decomposition. Right? Have a master problem on x, then fix x, solve the subproblem, generate a cut corresponding to extreme points or extreme rays, and then add the Bender's cut back to the master problem, and you keep iterating. So how do we translate this problem to problem with complicating constraints instead? The original formulation has complicating variables, right? We can do a simple trick to translate this problem to a problem with so-called non-anticipativity constraints. Right? So this is a reformulation trick in two-stage stochastic programming. Okay? The idea is the following, right? So since you know that x is a complicating variable, right? What if we create a copy of x for each scenario? Right? Then you can have an x for each scenario. Right? Both x and y are copied for each scenario. Then, but if you do this copy, you still have to make sure that all the copies of x are identical. Right? You have a unique first stage decisions to make. So therefore, you can add this constraint. So let's suppose x omega 1 represent the copy you make for scenario 1, and x omega 2 is the copy of x you made for scenario 2, and so forth. X omega, this capital omega variable, means the copy you made for your last scenario. Right? Now, if you add this set of constraints, which saying that all the copies you made has to be equal to the copy you made for the first scenario, then basically all the copies are equal to each other. Right? So with that, you will translate the original problem with complicating variables to this problem with complicating constraints. Okay. You look a bit confused. Any questions? Okay, so let's go to the next slide, right? So the original formulation where you have x, right, for the first stage, but now you create copies of x for each scenario omega here, right? But since the x is unique, right, just like let's say in the news vendor problem, the news vendor has to commit to buy this number of newspapers at the beginning. You cannot have different x for different scenario. Otherwise, you have like perfect forecast in the future, but you don't, right? You have to make sure all the x copies you created for each scenario are equal to each other, right? So this is so-called non-anticipativity constraint, meaning that at the beginning, the news vendor cannot anticipate what will be the real demand on the following day. So you have to add this in, such that the x is non-anticipative. Yes?
So is this also like assuming a uniform density of each scenario? Like each scenario is just as likely to happen as the other ones?
Yeah, so this is independent of the probability of the scenario. Right? So you can add a probability tau omega assigned to each scenario. The probabilities can be different, but the decisions you made at the beginning has to be the same for each scenario because you cannot anticipate at the beginning what will happen at the end.
Okay, so like in the case of the newspaper problem,
yeah,
what is x representing?
X is so now initially x represent the number of newspapers you buy, right? But now you are duplicating x to say I create a variable, say the number of newspaper I buy for different scenarios. Let's say the demand is from 100 to 200. There are 101 scenarios. So you create a number of newspaper you buy for each of these 101 scenarios. But you have to make sure they are the same, right? Because you cannot know which one of these 101 scenarios you will encounter. Therefore, you add this constraint to say each of the scenario has to be equal to the decision you add for the first scenario. Okay. Yeah, that's just a reformulation trick. It's equivalent to the original problem, right? The trick is to help you convert a problem with complicating variables to a problem with complicating constraints. Right? So now the x are no longer complicating variable because you created a copy for each scenario. Right? So now you have these complicating constraints instead. If you remove this constraint, then all the problems are decomposable by scenario. Okay. So with that, you convert the problem to this particular form, right? You have created a copy of x omega and for each of the scenario. Therefore, the columns of this constraint matrix will involve x omega, y omega, and so forth. And these are the constraints in the second stage, which are decomposable, right? What makes this problem non-decomposable are those so-called non-anticipativity constraints, right, which involves all the scenarios. Essentially, it is this constraint, right, that complicates the problem. Okay. So this is a problem with so-called complicating constraint. The idea of Lagrangian relaxation is it will dualize this complicating constraint and then make the problem decomposable. Any questions here? I see many people look very confused. No? Okay, so now if you are confused, you can go back again to take a look and do the reformulation yourself. Now let's assume if you don't follow, let's go to the next application, right? Don't keep thinking about this, then you will lose your attention for the next slide as well. So let's give you a different motivating application called generalized assignment problem. Okay, so this is a problem with complicating constraints as well. The idea is you want to assign job J to machine I with capacity Bi. Right? So each of the job, let's assume you have different number of jobs, and then you have a given number of machines. Right? Each of the job has to be assigned to one of the machine, which is represented by the xij variable. So xij is a binary variable, right? So for each of these, each of the job j, the job has to be assigned to exactly one machine, right? That's why you have this assignment constraint, the summation of xij equals to 1. Okay, that is an assignment constraint. And for each of the machine, you have this type of knapsack constraint, saying that for all the jobs that are assigned to machine I, right, which is represented by the summation over aij, xij, where aij represent the capacity it will consume, a given job will consume. Right? So if you sum over all the capacity of the job assigned to machine I, they have to be less than equal to the capacity of machine I. Okay? So we have a set of assignments constraints and a set of knapsack constraints. Okay. So one of the ways you can make this problem decomposable is let's dualize the assignments constraints. Right? So if you dualize the assignment constraint, right, you create a Lagrangian multiplier and multiply each of these assignment constraints by the Lagrangian multiplier lambda j, then you end up with this particular problem. Right? Where you removed, essentially you bring this assignment constraint to the objective, right? And you are left with the knapsack constraints here, right? Now with this trick, you can find out that each of the knapsack or each of the machine is decomposable, right? After you dualize the assignment constraint, then each of these problem is decomposed by I, right? Since all those constraints are separable already, right? You can gather the xij variables that are related to I in the objective and solve a knapsack problem separately for each machine you have. Yes.
When we dualize it like that, isn't that equivalent to just adding essentially a penalty? And so then would this restrict us to only using interior point methods?
Yeah, so that's a good point, right? You intuitively you can think about bringing the Lagrangian as adding a penalty, right? If you violate that constraint, the Lagrangian should ideally penalize a violation of the constraint. But now I haven't discussed how do you choose the penalty. Right? That's what Lagrangian relaxation algorithm is going to tell you. Here I'm just using a motivating application saying that if you can penalize them by a Lagrangian penalty, the problem becomes decomposable. Right? So then we will cover what penalty you should choose and how do you choose them. Yeah. Now, so with this Lagrangian dual multiplier, you can find out that you can decompose the problem by machine I, right? So this is nothing but I did this dualization, and then I rearrange the coefficients by machine I, right? So essentially you have a sum over I sum over j, right? You can separate them by each machine I, right? Essentially you want to separate this summation over I, and then you have a knapsack problem to solve for each of these subproblems, right? So you could reduce the size of the problem by the number of machines. For each of the machine, you have a knapsack problem where you could solve it using an MILP solver. You could also solve it using things like dynamic programming. Okay. Yeah. So this just to give you two different applications, saying that for some of the problem, if you can identify a set of complicating constraints, right? After you remove or dualize those complicating constraints, the rest of the problem becomes easy, right? In this case, it's like the rest of the problem can be decomposed by subproblem. In the two-stage stochastic programming case, the subproblems are decomposed by scenario, right? In this machine assignment case, each subproblem corresponding to a knapsack problem for each machine I. Right? There are other applications with this structure as well. Okay. Yeah. Now, with that, hopefully it convinces you that there are meaningful applications where you would like to deal with problem with complicating constraints. So in the next few slides, we will present Lagrangian relaxation in a more general framework. Right? I will simplify the notation quite a bit so that this presentation is general for any problem. Right? Here, let's define the problem as follows. Where you have a MILP problem. Okay, so where all the x are mixed integer. Let's assume you have some binary variable, some of the x are real variables. And then you have two sets of constraints, ax less than equal to b, ex less than equal to d. Right? So these are just general linear inequalities. They can occur in different applications, right? So in these applications we just defined, you can think about ax less than equal to b as a complicating constraints. So in the stochastic programming case, the complicating constraint ax equals to b, less than equal to b represent those so-called non-anticipativity constraints, right? And in the in this machine assignment problem, you can think about ax less than equal to b represents those assignment constraints. So the ax less than equal to b are assignment constraints. And then ex less than equal to d represent the so-called easy constraints. Right? So the idea is if you can remove these complicating constraints, the rest of the problem are easy in the sense that maybe ex less than equal to d has a decomposable structure. Right? But we are not representing that decomposable structure. You can assume it has a decomposable structure inherently. Yeah.
I guess I'm still confused on how we identify what's complicated and what's like an easy constraint.
Yeah. So here in the two motivating application, would that clear to you? Because if you remove that constraint, the rest of the problem are decomposable. That's why we call those decomposable constraints easy constraints.
So basically, if you're able to, I guess, like generalize those constraints and separate the problem into a lower class of problem, it's easier to solve.
Yeah.
That's a complicated constraint.
Yeah, so if you remove those complicating constraints, the rest of the problem becomes easy, right? Maybe usually it's because they have a decomposable structure.
Okay.
Yeah, so these are called easy constraints because they have a decomposable structure. You can run them in parallel. Okay, yeah. Okay, so this is a notation we will follow, but in practice, you can think about the two applications we have, right? They represent the complicating and the easy constraints. Now, the idea of Lagrangian relaxation is closely related to Lagrangian dual. Right? Hopefully, you still remember the Lagrangian dual we covered in the first half of the semester. But if not, I will remind you real quick. Okay. So here, again, the idea of taking the Lagrangian dual is you create a non-negative Lagrange multiplier for the complicating constraint to dualize them, right? So this is like a Lagrangian dual function. For a given lambda, right, you dualize the complicating constraint. And in this problem, it is a minimization problem over X, right? Again, intuitively, you can think about lambda as a penalty on violating these inequality constraints, right? So here, lambda is greater than or equal to 0. The reason is because in the original constraint, we have a less than or equal to 0 constraint, right? That's why lambda is greater than or equal to 0. Remember, if you have equality constraint, then lambda should be unrestricted, right? And if you have less than or equal to constraint, lambda should, if you write it, if you have greater than or equal to constraint, lambda could be less than or equal to 0. The idea is that you have to make sure this part gives you a lower bound, right? That is what we tested in the midterm exam. The size of the lambda has to be consistent with the primal constraint in order to give you a lower bound, okay? Yeah, so if you recall, as long as the signs are consistent, no matter what constraints you have, the d lambda is a lower bound of the primal, right? Just by definition, the ways we define those signs of lambda and the way we define those constraints, you can show that this for any of the lambda greater than or equal to 0, the d lambda is a lower bound of the original problem, right? And you probably still remember the Lagrangian dual is defined as the lambda that give you the tightest lower bound, right? So since for each lambda greater than or equal to 0, d lambda is a lower bound, and you are interested in providing the tightest lower bound possible, right, using the Lagrangian dual, right? So this is essentially the dual problem, right? And remember that for convex problems, strong duality hold, right? Meaning the Lagrangian relaxation equals to the value of the primal problem for convex problem with some constraint quantification. That kind of is a way we motivate algorithm like interior point and so forth, right? Now, what about non-convex problem? In the problem definition we just gave you, it is clearly a non-convex problem. You have integer variables. So in general, you will have a non-zero gap for non-convex problem. Okay, so you can only say the Lagrangian relaxation is less than or equal to the value of the primal problem. But then what is this gap? It is not so clear to us at this point. Okay. Yeah, let's see, any questions at this point? Yeah. So now let's motivate the so-called primal characterization of the Lagrangian relaxation. Again, back to this slide, right? But, we know that for convex problem, you have strong duality, right? But then for non-convex problem, the only thing you know is the Lagrangian relaxation is less than or equal to the primal problem. But then how are they related, right? How are these two values related? So that motivates the so-called primal characterization of Lagrangian relaxation. The idea is if we can characterize using the primal constraint, how tight is the Lagrangian relaxation, right? Then it gives you some idea on how good this relaxation is. Or maybe you want to answer questions like, how does it compare with the linear programming relaxation for MILP? Right? You construct a Lagrangian relaxation, and now you may wondering how good is this relaxation, right? Is it better than the LP relaxation, or is it worse? Okay. So now let's show a theorem which gives you an idea of how tight this Lagrangian relaxation is. Right? So this so-called primal characterization of Lagrangian relaxation, it is equal to the following, right? So the value of the Lagrangian relaxation is equivalent to solving the following primal problem, right? So that's why it's called the primal characterization, because in this optimization problem, there are no dual variables, right? We are representing the value of the Lagrangian relaxation using the primal variables only. Okay. So you have the original linear constraint, the complicating constraint you dualize. And the other constraint we have is the convex hull of the constraints we did not dualize. Okay, so let me go back to the original formulation, right? So in the original formulation, you can treat the original formulation as two sets of constraint. One set of constraint is this linear complicating constraint. The second set of the constraint is a constraint you did not dualize, right? Those linear constraint plus some integrality constraint. So x equals to capital X is some integrality constraints. You can treat them as the constraint you did not dualize, right? And ax equals less than or equal to b are the constraints you dualized. Okay, and then what this theorem says is the Lagrangian relaxation will give you the following, right? It gives you the ax less than or equal to b has to be satisfied, and x also has to satisfy this set of constraints, saying that x is in the convex hull of ax less than or equal to d, and x being mixed integer, right? So essentially, in words, it says the Lagrangian relaxation is equal to solving the problem constrained by, here I wrote it here, the convex hull of the constraints that are not dualized intersected with the constraints that are dualized. Okay. So here, essentially, you have two different sets of constraint. The first set is the constraint you dualize, the complicating constraint ax less than or equal to b. But for the constraint you did not dualize, it will not be exactly in this constraint, right? Because if you have x is in ex less than or equal to d, x equals to x, if you have this set of constraint, it's equivalent to the original problem, right? But if you do Lagrangian relaxation, you are relaxing this set of constraints by its convex hull. Okay, so that's why you can say it is a relaxation, right? Because you are relaxing the original set of constraint by the convex hull of this set of constraints. And this is true for any non-convex set X. Okay, and we will show a proof for MILP representable constraints. Now, before I show the proof, because the proof will perhaps make some of you fall asleep, let's see if I have any questions. Yeah.
So this says that it's for any non-convex set X. Wouldn't it also work if X is convex?
Yeah, for sure. Yeah. If X is convex, that for sure works, right?
And same with our complicating constraints. Those constraints are also, those can be convex or non-convex.
So for convex set, it's very trivial, right? Because if this set is convex, then the convex hull is the set itself, right? Yeah. So that trivially holds.
If our set for AX is less than or equal to B, so the complicating constraints, if those are also, does this work if they're convex or non-convex, or do they have to be
I see,
convex for the AX is less than or equal to B?
I see. Yeah, that's a good point. I'm not so sure. Okay, yeah, I will try to get back to you. But at least they work for the AI, for linear ones, right? We will show a proof for the linear ones. Yeah. Okay. Now, before we show the proof, as I said, the proof is a little bit technical. It's actually not that hard. So let's try to kind of interpret this theorem a little bit, right? So with these theorems, can you say something about the Lagrangian relaxation compared with the linear programming relaxation? Is the Lagrangian relaxation in general better than linear programming relaxation or worse? Yeah.
Wouldn't it be closer than the linear programming? Because the Lagrangian relaxation, we're not touching the bounds of the AX is less than or equal to B. Those are essentially staying consistent.
Yeah,
We
yeah.
just reformulated them, whereas with the linear programming relaxation, in every case, we are changing the overall bounds of all of our constraints.
Yeah, that's a good intuition, right? So you could say something like, if you do the linear programming relaxation, you are just relaxing this set using its LP relaxation, right? So this is a mixed integer linear programming set, right? So if you do the LP relaxation, you just do the LP relaxation for this set. But of course, this linear programming relaxation is weaker than the convex hull of a mixed integer programming set, right? The best convex set you can get is a convex hull, right? Yeah. So, but then is it the same thing as the original problem? Or is it weaker than the original problem? Why it is weaker than the original problem?
Well, we don't have integrality constraints, so we can get like fractional solutions.
Yeah. So the ways you can see that is if you want to get the value of the original problem, you should take the convex hull of all the constraints. Right? So if you want to get, remember we have a theorem saying that if you want to get VP, then you should do minimize X, C transpose X, subject to X is in the X is in the convex hull of all the primal constraints. Right. This is something we showed in previous lecture, right? That motivates us to develop things like cutting plane. Right. If you get a convex hull of the original feasible region, it is equivalent to the original problem, right? So how is this set, the convex hull on the original problem, differs from this primal characterization?
Well, we still got like AX less than equal to B naught.
Yeah. So this is a case where you are convexifying the whole feasible region compared with you partially convexifying a subset of constraints, right? Of course, convexifying the whole feasible region gave you a tighter relaxation, right? So this is the intuition here. So let me show you, maybe before showing you the proof, let me show you a geometric intuition on this problem, okay? Now, so let's assume this is your complicating constraint, right? It's a linear constraint denoted by AX less than or equal to B. And this is your constraint denoted by EX less than or equal to D, right? And you have some integrality constraints, okay? Now, the feasible region of the original problem are the integer points. So the feasible region for the original problem are the integer points within the two sets, right? Because you have to satisfy the integrality constraints. You have to satisfy the two polyhedral constraints, right? So the feasible region for the original problem are all the integer points in this set here, right? And let's suppose you are minimizing Z, okay? And, okay, so in this case, maybe the plot is showing, yeah, so you are minimizing over this Z direction here, right? So Z is increasing here, you are minimizing Z. And then this particular point will be the optimal solution of the original problem, right? Because you need to satisfy integrality constraint, they have to be in the intersection of the two polyhedral set. Okay, so this is the original problem, the value of the original problem. what is the value of the LP relaxation? It is very easy, right? Because it is just one of the extreme points of this polyhedral set, which is this point here, right? That minimize the LP relaxation. Okay. Now, what is the optimal solution of the Lagrangian relaxation? Right. Remember, the primal characterization tells you it is a convex Hall of the constraints you did not dualize, right? So the constraints you did not dualize are these linear constraints plus the integrality constraint, right? So the convex Hall of the constraint you did not dualize are this shape in the dashed line here. Okay, so this is the convex Hall of the constraints you did not dualize. And then you have to use this convex Hall to intersect with the AX less than or equal to B you dualized, right? So what this intersection gives you is this particular region here, right? So the Lagrangian relaxation's feasible solution is this particular region, and the optimal solution is this point here. Okay.
Sorry, are we maximizing or minimizing?
We are minimizing. So let's say this is Z is increasing here, but you are minimizing. Yeah. 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 Yeah.
So in this case, whenever you look at like the region of the convex of X or of S and our other region,
Yeah.
why doesn't it find like the, I guess, optimal solution to the whole problem, since that's also an extreme point on that shape?
Yeah, so you are just taking the convex Hall of the constraints you did not dualize, right?
Yes.
So it is, I mean, if you find an extreme point on this shape, it's integral, it satisfies the integrality constraints, right?
Yeah.
This shape is cut by this shape you did dualize, right?
Yes.
And if you consider their intersection, right? So their intersection is this region, which this new extreme point you created by intersect with a complicating constraint may not be integrality constraint anymore, right?
Okay.
So if you do the intersection, the new extreme point you created may not satisfy the integrality constraints anymore,
Okay.
right? So the convex Hall, these extreme points of convex Hall of S do satisfy the integrality constraints. But after you cut this convex Hall by AX less than or equal to B, then the new extreme point you got may not satisfy the integrality constraints. Yeah, you have a question?
Yeah, so this is showing that the Lagrangian relaxation is a stronger
Mm-hmm.
relaxation than the linear programming.
Yes, yes, yeah, yeah.
Just want to verify that.
Mhm, yeah. Okay, now I don't think I have enough time to go through the proof. Let's skip the proof for now. You can just believe this is true. And then if I have the time, I will come back to it, because I do want to finish, at least you know how to implement these methods, right? So the proof only relies on the Mayer's theorems and linear programming duality. Yeah. Okay, so the next step, let's talk about how do you solve the Lagrangian dual, right? Essentially, what I'm talking about is, here. So how do you solve this maximization problem, right? You want to find a lambda that maximize the relaxation you created, right? So does anyone remember what we did for convex problem, or for some special case of convex problem? Like for linear program, what we did to get the Lagrangian dual? Is it too easy or too hard? Again?
Can you ask the question?
Yeah, so how do you find the dual of a linear program?
Just pick the cost and
Yeah, so you take the dual, it has a closed form, right? You can solve give you a primal, take the dual. What about the Lagrangian dual for quadratic constraint quadratic programs?
you get the SPP for
Yeah, right. Yeah, you derive the Lagrangian dual in closed form as well, and it happens to be an SDP, right? So for this special case, you can derive a closed form, right? So does the Lagrangian dual of a mixed integer linear program has a closed form, right? We do not know that, right? So actually, until this point, we still do not know that. So right. But if you can do that, you can publish a very nice paper. Right? Yeah. Yeah. Okay. Yeah. So that's why since we don't have a closed form, then we need an algorithm to get the Lagrangian dual for problem that does not have a closed form Lagrangian dual. Right? So problem like mixed integer linear program. We will use mixed integer linear program as a motivating problem, but most of these methods I showed you will in general hold for many different types of problems. You have a question? Yeah.
Yeah. Sorry. The reason why there's no closed form is because effectively, like, we can't take the Hessian. Is this like that?
Not really. So recall, let's say in the case of QCQP, right? What we did is we first check under which condition the problem is bounded, when it is unbounded, and so forth, right? And when it is unbounded, you take the derivative and try to find a closed form solution,
Okay.
right? But for more general problem, for mixed integer linear program, is not even differentiable. Right? You cannot just do the derivative and set that. Okay. Yeah, so this is finding Lagrangian dual for QCQPs, right? This is nice because the Lagrangian dual is an SDP. But then for mixed integer linear programs, it's not that trivial. Right? The reason is that the d lambda is essentially a value function of an MILP. Recall we talked about the definition of value function before. Right? It is essentially given a given value lambda, you have to solve an optimization problem to get the function value of d lambda. And the value function of MILP is very hard to express in closed form. Although there are some theory related to that, but computationally those theories usually don't work very well. Okay, now the idea is we will need something like an iterative algorithm to find the optimal solution for maximization problem over d lambda, right? So we will talk about two methods to solve this maximization problem. One method is very closely related to gradient descent or gradient ascent. The other method is like a model-based method called cutting plane method. Okay. Now, before we present the two algorithms to solve d lambda, let's try to analyze the properties of d lambda, right? So that's what we have been doing over this course, right? Whenever you solve an optimization problem, whenever you want to come up with some new algorithm, you want to know the property of the problem you are dealing with, right, before you design a tailored methods. So here is also the case, right? We want to study the property of d lambda, whether it's a continuous function, whether it's a differentiable function, or is it a convex function, or in the maximization case, it's whether d lambda is a concave function, right? If minimization, you are interested in convexity. Maximization problem, you are interested in whether the problem is concave. So here's some proposition on the properties of d lambda. So again, we are maximizing d lambda, right? So if it's concave, we are in a very good shape, right? So d lambda is concave, continuous, piecewise linear, and non-smooth, right? So here's a very simple proof of the property of d lambda. Okay. So again, d lambda is nothing but the minimization problem of C transpose X. You have a lambda times the complicating constraints, and then all the constraints are MILP representable, right? Now, since we are interested in the objective function d lambda only, right? So whenever you are minimizing over a linear function over some linear constraints, right? We know that this is equivalent to minimizing the same linear objective over the convex hull of the constraints, right? So this S means the this feasible region described by this constraint, right? So let's denote them by the convex hull of this constraint here, right? And then we also know that from what is called the Mayer's theorem. It is a fundamental theorem of integer programming. It says if all the numbers E and D are rational numbers, then there exists some polyhedral set that can represent the convex hull. Okay, I actually have that theorem in the slides. Let me show you real quick. It is in the proof. So this is something called Mayer's theorem. We discussed before in the lecture of cutting planes. Okay, just to refresh your memory. What it says is, given a rational matrix E and a rational vector D, right, that S equal to the mixed integer linear constraints, where this capital X set means some of the variables are binary, some of them are continuous. So if E and D are rational, then Mayer's theorem says there exist rational matrices H and a rational vector H, such that the convex hull of this mixed integer set can be represented as a polyhedral. Right? It is called the fundamental theorem of integer programming. We did not prove that, but you can assume it is true. Right? In words, it's like for most of the mixed integer linear program, assuming you represent all the numbers using rational numbers, it's not a very restrictive assumption, right? Because all the rational numbers are dense enough in the as close as possible to any real numbers you want to approximate. Now, with that, you can see that for any MILPs, you can represent its convex hull as linear constraints, right? So that's what this Mayer's theorem says. Okay. So that's why if you want to represent the convex hull, then you can replace them by hx less than or equal to small h. Okay. Now, if you are minimizing a linear function over a linear inequality, it's a linear program. Right? If it's a linear program, you know that the optimal solution is obtained at one of these extreme points. Let's assume this problem is bounded. It's not a so restrictive assumption. If it's bounded, then essentially this minimization problem is equivalent to picking all the case where k being the extreme points of this polyhedral set hx less than or equal to lowercase h. Yeah.
How does this? I thought we were trying to solve for our lambda.
Yeah. So that's a good point. Again, so the logic here is a little bit complicated here, right? Before we solve for the optimal lambda, we want to analyze what property this function d lambda has to satisfy, right? So we want to know whether d lambda is convex, whether it's continuous, it's smooth, and so forth, right? So here this theorem is to say the function d lambda is a concave, continuous, piecewise linear, and non-smooth function. Right? Once we know the property of this function, we can design an algorithm to solve for the optimal lambda. Okay. Yeah.
I have a stupid question. Our x has some real and some integer variables.
Yeah,
right?
yeah.
But do we know anything about lambda? Is it real number or is it only integer?
Yeah, so lambda is real, right? Because you are dualizing the complicating constraint. So lambda is any non-negative real number, right? Okay. You can assume the original constraints are mixed integer. Like,
So it's always real.
Yeah.
How would you solve that minimization problem if we don't know the value of lambda? I feel like we want to know lambda, so we solve another problem that still has lambda in it, so now we don't know how to.
Yeah. So again, so this part is not try to solve for the optimal lambda or solve for the optimal x. It is like a theoretical analysis on the property of d lambda, right? So you can here none of these steps are what we are going to implement. Okay. These steps are just to show you theoretically d lambda has to satisfy these properties. Then once we know this theoretical property, we can develop a more practical algorithm to handle that. Okay. Yeah. Okay. Yeah. Thanks for asking. Any other questions? Okay. Now, Now with that, theoretically, d lambda is essentially a minimization problem over a set of extreme points, right? So if you have the set of extreme points, then you can show that the d lambda have to satisfy these properties, right? Because essentially this operation is taking the minimization over a finite set of linear functions with respect to lambda. Right? So if you pick any of the extreme point, it is a linear function of lambda, right? And then you are, this d lambda function is the minimum over capital K number of linear functions, right? So how does this function look like, right? Remember the way the convexity analysis and so forth works is that if you take the minimum over a finite number of linear function, you get a concave function, right? And remember, if you take the maximum over a finite number of linear function, you get a convex function, right? So if you don't believe that, you can sort of remember this picture here, which gives you the geometric intuition. Of course, you can show that mathematically as well, right? Here's a three linear functions. Let's assume we have three linear functions over lambda, right? And you want to take the minimum of these three linear functions. That is essentially this function here, right? And this function is clearly a concave function from the picture. You could show that mathematically as well, okay? So with that, we can see d lambda is the minimum of finite number of linear function, right? It is concave by what we studied before, right? So that shows the concave property, right? And since this minimization over linear function, of course, is piecewise linear, and then it is also continuous, right? But the thing is that this function is so-called non-smooth because it's not differentiable everywhere, right? At these points, the function is differentiable. If you move to a point where two linear functions cross with each other, at this point, the function is no longer differentiable. Right? That's called a non-smooth problem. And if you recall, what we talked before is that for non-smooth function, you cannot get a gradient, but you can get what is called a subgradient. Right? So we will talk about that later on. Now, with this property of the Lagrangian function, then you will know what method you are going to use, right? So because it is a non-smooth continuous problem, and it is a maximization problem over concave function, right? So maximization over concave function is equivalent to minimization over convex function, right? So it is essentially a convex problem, but the tricky thing here is that it is non-smooth, right? So there is a research area called non-smooth convex optimization, where they study how do you solve non-smooth problem, but if the problem is convex, how do you solve that to optimality, right? So here, since we d lambda satisfy this property, we can refer to any algorithm that deal with non-smooth convex optimization problem, right? So since non-smooth convex optimization is a general problem, right? We don't need to worry about whether the original problem is mixed integer or is something else, right? As long as we know d lambda is a non-smooth convex problem, then we can use any non-smooth convex optimization methods out there in the literature, okay? So here I'm going to introduce the two most basic algorithms for solving non-smooth convex optimization. They are called cutting plane method and subgradient method. Okay. So let's start with the cutting plane method. So the idea is very similar to the cutting plane algorithm we developed before, right? Remember in outer approximation, Bender's decomposition, or even column generation, the idea is we start with a small subset of the cutting planes corresponding to the extreme points, right? And then if we find out some of the cutting planes are violated, we will add that back to the master problem. Right? In outer approximation, it's also the case. We start with a relaxed MILP and find the integer solution. If we find some of the outer approximation cuts are violated, we'll add it back. Right? So it's the same idea here. Right? So we can define a so-called Lagrangian master problem. We know that the objective is a minimization over cuts in this shape, right? So if you have all the cuts corresponding to the extreme points, this is equivalent to the original problem, right? Because you are essentially trying to find a lambda that maximize this problem where the objective is a minimization over all the extreme points, right? So that is, this objective should be less than equal to all the linear function, right? So the eta here is less than equal to all the linear function you have, right? You are minimization over all the linear functions, but you are trying to find the lambda that maximize this minimization over linear function, right? So this is a reformulation of the problem we have, where K is a set of all the extreme points in the convex hull. Right. The issue is that, of course, you don't know how to get all the extreme points of the convex hull. Right. It's a super expensive problem. Now the idea is you start with a Lagrangian master problem where let's assume this set K0 is a very small subset of all the extreme points. Right. You could warm start using some of the extreme points. Now let's denote this solution to the master problem as eta 0 and lambda 0. Now the next step is to find the extreme points corresponding to the most violated constraint. Okay, so again, initially, if you want to do the exact formulation, you need this set K with all the extreme points, right? Now you are starting with a small subset of extreme points, right? If you can satisfy all the constraints in the extreme point, then you are done, right? But the thing is that when you start with a small subset of extreme point, there usually will be some of the constraints you are violating, right? With the solution eta 0 and lambda 0. Now the next step is we want to find out the most violated constraint, right, in the set of extreme points. So how do we find such an extreme point which most violated the constraint, right? Yeah.
By most violated, do we mean like the furthest from the constraint?
Yeah, so let's say you can write this constraint as eta minus C transpose xk plus lambda transpose axk minus b, right? So this is a single constraint. It has to be less than equal to 0, right? So this is nothing but a rewrite of this, moving it to the left-hand side. By most violate is, if you evaluate each of these constraints, they should be less than equal to 0, right? The most violated one is the one that gives you the largest number, right? Okay. Probably for one of the xk, this number is much bigger than 0. That means this constraint is violated. Right?
So basically, like you would loop through each set of numbers, and
yeah.
you would just be like,
yeah.
what are the largest ones?
Right. Yeah. So the naive way is you just loop through all the extreme points, right?
Mm-hmm.
But the thing is that you don't know all the extreme points in the first place, right? They are MILP representable. So how do we sort of solve a subproblem to find the most violated extreme points? Right. So this is very similar to what we did before, right? Remember, in column generation, you will find a column that give you the most negative reduced cost, right? Now here is like a cut generation instead of column generation, right? But in that case, you want to find the most negative reduced cost. Here is like you want to find the most violated constraint, right? So how did we find the problem? How did we find the column with a negative reduced cost?
We found the columns with the knapsack problem. problem.
Yeah, exactly, right. So that's in the, what is that? Like cutting set type of applications, cutting stock applications. But in the Danzig-Wolf decomposition, how did we generate that column, right? Can we borrow some ideas here? Because I told you at the beginning, Danzig-Wolf and Lagrangian are a dual of each other, right? So essentially here, instead of solving a pricing problem, you will be solving a slightly different problem, but they are actually a same problem, right? Any thoughts there? Okay, yeah. So in order to find the problem with a most violated constraint, you might want to recall where those extreme points come from, right? So again, if you go back a few slides, the extreme points of this constraint come from the original constraint you did not dualize, right? So the extreme points are the convex hull of the original constraint. They are, in other words, they are feasible for the original constraint, okay? So what you could do is solve a maximization problem to find the most violated constraint, okay? So the way you could do that is you could maximize, if you, let's say, if you maximize xk, right, such that xk has to satisfy the original constraint. Right. So with that, you will find the so-called most violated xk. Right? Since xk is nothing but a point in satisfy the original constraint. Yeah.
How is that different from just enumerating all the possible?
Yeah.
Because that's kind of what that's doing, isn't it?
Yeah. So if you want to enumerate all the extreme points, well, it could be very difficult, right? You don't even know all the extreme points. So here, but algorithmically, if you solve this maximization problem, you can use a MIP solver like Ruby to solve this MLP. Right? You are using branch and cut to find out the most violated extreme points. Right? Enumeration of overall the extreme point is extremely hard. Right? You don't even know where they are. But you know that if you solve an MLP using Ruby, it actually will terminate with n extreme points of the convex hull using branch and cut. Right? So if you want to get a convex hull, you are essentially solving an MLP with pure cutting planes. It's not efficient. Right? So the more efficient method is to use branch and cut. Yeah.
And I guess like like for example, the lambda that you use would be lambda naught in the maximization problem.
Yeah. So you are keeping the lambda naught. Yeah. Very good point. Yeah. So here, as you already suggested, you are going to use the lambda naught you just find out, right? And the eta naught to see if you can find any violated constraint using the current lambda naught and then eta naught. But then what you are interested in finding the most violating k. But a naive approach, you want to enumerate all the extreme points, but it's not tractable. The tractable way is you solve a minimization problem with this MILP constraint, then you can call a solver to find the most violated extreme point. Right? Yeah. So here it is a minimization problem over the easy constraints. Right? So this problem is called the Lagrangian subproblem. If E has a decomposable structure, this problem is also decomposable. And then, the solution is an extreme point. Right? If you find the most violated constraints are still satisfied, then this cutting plane method will converge. Otherwise, you add the x0 to the master problem and keep iterating between the master and subproblem. Okay. Yeah. So geometrically, what does the cutting plane method do is, let's say you start with Yeah, so let's say you start with these two cutting planes, and you find out the optimal lambda here, right? And you, with this given lambda value, you find a violated cutting plane, you add it back until you find out there are no longer violated cutting planes, then you are done, right? So cutting plane method is essentially a model-based method, right? You are solving a problem where you want to represent the function as a minimization over all the constraints. You start with a small number of constraints, and once you find out some of the constraints are violated, you add them back until you find out that no other constraints are violated. Okay. Yeah. Now, another thing you can try to do is, I will leave that as a homework question. You can find out the Lagrangian master problem is a linear programming dual of the Danzig-Wolff master problem, right? So in the Danzig-Wolff master problem, each extreme point corresponds to a column, right? So in the in the Lagrangian master problem, each extreme point corresponds to a constraint, right? So that sort of gives you an intuition why Danzig-Wolff master problem is the LP dual of the Lagrangian master problem. And they are dealing with problem with the same structure, right? The same structure being that you have some complicating constraints. Okay, so with that, let's go to the second algorithm called subgradient method. Let's review quickly what is a subgradient, right? So subgradient is used for problem without a gradient, right? And if you have a convex function, right? Remember, we gave you an example of this absolute value function. It is clearly a convex function. At these points, the gradient equals to 1, but at this x equals to 0, this function is non-differentiable, right? But subgradient means you need a vector g such that the function is lower approximated by the first order. It's like a first order Taylor series expansion using the subgradient here, right? So at this particular point, what is a valid subgradient here? It is anything between -1 and 1 that can under approximate this convex function, right? So therefore the subgradient here is from -1 to 1. Right? So if you look at this form, it's very similar to the first order characterization of a convex function, right? You need to have some linear under approximation of a convex function, right? For a non-smooth convex function, you can think about the g as a generalization of the gradient, right? As long as this linear approximation under approximate this is like a linear approximation and it under approximate the original function. And then there is also a definition called supergradient, right? For concave function, you need a sort of a linear function that over approximate the concave function, right? So like the minus minus absolute value function, you can show that the supergradient is also from -1 to 1, right? So the takeaway here is that supergradient is for convex functions, supergradient is for concave functions, subgradient is for convex functions. Okay. Any questions on the definition here? All right. Now, with that, we can do things called subgradient method. Right? It's very similar to so-called gradient descent. Okay. The idea is the following, right? At a given point in d lambda, right? Since we know d lambda is a piecewise linear function, we want to maximize a piecewise linear function. Then you can do what we call supergradient ascent or subgradient descent, right? You want to maximize a concave function, then you can move along the supergradient direction. Now the question is, how do we get a supergradient for the function d lambda? Now here's the proposition says that a supergradient at a given point lambda 0 is nothing but ax0 minus b. Right, where x naught is the optimal solution of the Lagrangian subproblem. Okay, so this might sound a little bit confusing. Here, let's think about this problem in a more geometric way. Right? Now, let's pick a given point. Right? So let's assume this is a d lambda function, which is defined by the minimization of 3 linear functions. Okay. Now, if I pick a point, let's call it lambda 0. Right? What is the subgradient or gradient at this point lambda 0? Right, using the notation I have in this figure. Yeah, so the subgradient at this particular point is nothing but, let's say, s equals to ax3 minus b, right? Because the ax3 minus b is essentially the gradient of the lambda at this particular line, right? So how did I pick ax3 instead of ax2 and ax1, right? Because the reason I pick ax3 is because at this particular point, ax3 gave you the minimum value, right? That's why I pick ax3, right? So it is because x3 is the optimal x at this particular point, lambda 0. Right? If you pick 2 or 1, it will give you a much bigger value, right? So since d lambda is a minimum over all the 3 linear functions, you are going to pick ax3 as the ax3 minus b as a subgradient. Okay, so that's sort of the geometric intuition here. Yeah.
So if our lambda 0 is actually where our y star is?
Yeah. Yeah. So then it could be degenerate at this point, either ax2 minus b or ax3 minus b. They are both subgradients. Right. Yeah. Okay. So the argument here is at any given point lambda 0, the corresponding ax0 minus b is a subgradient of the function d lambda. Okay, and then you can show that in a more rigorous way, where d lambda is essentially defined as a minimization over all the extreme points. Right, for any given lambda, it is a minimization over all the extreme points, and it must be less than or equal to when you choose the point x naught. Right? For any given lambda, because you are taking the minimum over all the k extreme points, it must be less than or equal to one of the extreme point x0. Right? Then you can rearrange this notation a little bit, and you will get here d lambda 0 plus s0 lambda minus lambda naught. Right, where you could this essentially gives you d lambda less than or equal to this part, and it shows x naught is a subgradient at lambda naught. Okay, so this is a very simple proof. So with the subgradient, you can use subgradient methods. It's very similar to gradient descent. Right? The only difference here is we are not going to do line search, because line search is quite expensive. In each step, when you solve a new lambda, you are solving a MILP. Right? That's why line search is quite expensive. So you can each step you need to solve a d lambda k to get the in this case it's a super gradient, and then you can do something like a gradient ascent by multiply the lambda by multiply the super gradient by a step size mu. So how do you choose the step size mu is not a trivial problem. One of the heuristics I outlined here is you can approximate mu by this ZU is an upper bound, eta is the current lower bound, and this is the size of the gradient, and multiply them by alpha, where alpha is typically chosen between 0 and 1, and is reduced by multiplying beta if it fails to improve. You can check the details of this heuristic, but there is nothing fancy here. If you want to implement that, you can use this heuristic to choose the step size. Now, so with that, I need to quickly talk about so-called Lagrangian decomposition. So Lagrangian decomposition is a reformulation of the original problem, where instead of dualizing this ax less than or equal to b, we create a copy of x for the two blocks, right? So that, let's say you create a y variable saying that the y has to satisfy ey less than or equal to d, and x has to satisfy ax less than or equal to b, and you implement the integrality constraint for both x and y. Of course, you have to set x equals to y, right, for this duplication. Now the idea is instead of dualizing ax less than or equal to b, you will dualize x equals to y instead by multiplying the Lagrangian multiplier v. Right. So this is nothing but a reformulation, very similar to the non-anticipativity constraint type of trick. Yeah.
When we dualize x equals y, do we also dualize the integer constraints?
No, just dualize x equal to y. Yeah. Okay, yeah. So with that, you could dualize x equal to y, and then you are left with these two sets of problem, right? Where you have a problem on x where you have the integrality constraint, but then you have v transpose x. V is a Lagrangian multiplier. On the other hand, you have a minus v transpose y, where you have the constraints on e y less than or equal to d and y are integer. So here the dual bounds are maximization problem over nu, right? This Lagrangian multiplier you introduced. So one interesting observation here is the Lagrangian decomposition gave you a tighter bound than Lagrangian relaxation. Okay. So how do we prove this proposition? Any thoughts? Right, this is nothing but a reformulation, and then you dualize the x equals to y instead. So a proof here is you could use the primal characterization we developed before, right? You can use this primal characterization we showed. Here, the primal characterization of the Lagrangian decomposition is, again, you are going to intersect the constraints you have dualized, which is x equal to y, with the constraints you did not dualize, right? And with that, what you will get is the convex hull of ax less than or equal to b, x satisfy integrality constraints with the other convex hull. Okay, so yes, yeah, and then with that you could show you get a tighter relaxation. Okay. Yeah, you can read a bit about it in detail, right? And this plot will give you a geometric intuition to show you that the Lagrangian decomposition is tighter, which is you need to intersect the convex hull of these two sets with integrality constraint, and that will give you an even tighter bound than the Lagrangian relaxation. Okay, so the other important question I need to talk about real quick is Lagrangian relaxation give you a lower bound, right? But how do you obtain an upper bound, right? That's sort of the dark side of Lagrangian relaxation. Is the lower bound is rigorous. You can always use cutting plane or subgradient method to get a lower bound, but you also need a feasible solution to the original problem that give you an upper bound. So in that case, we have to use some sort of heuristic. One of the commonly used heuristic is, let's assume you have the Lagrangian decomposition, you solve these two problems separately, right? But then after you solve these two problems, the x you got from this side may not be equal to the y you obtained from the right, right? But you need x equals to y in order to satisfy these complicating constraints. So one of the ways you could do is just you take the average of x and y you got from the two blocks, and then you run the integer variable to try to get a feasible solution. This is one of the most commonly used heuristics, but for a practical application, you can come up with different heuristics. What about convergence? Lagrangian decomposition applied to MLP has a non-zero gap, right? Because it's primal characterization, it gives you a non-zero gap. In practice, you can just apply some arbitrary heuristic, and then hopefully the heuristic works pretty well, and you get a very small gap, right? But if you want to get guarantee convergence, and you are really curious about that, you can check this paper by Carreau and Schultz. They combine branch and bound with Lagrangian decomposition to guarantee convergence. And similar property, of course, it also holds for Danzig-Wolf, right? I remember maybe Sergey, you asked, what if in Danzig-Wolf you still don't get the integer solution? Then you can do some branch and bound as well. This is called branch and price. Yeah, so here are some of the references you can take a look. Especially the integer programming textbook. This book published in 2003 is a very nice tutorial on Lagrangian relaxation. It has almost everything you need to know.